All right, time for example 4. So, as you can see by the title, we might be using polar coordinates, just maybe. All right, so we're given this integral, okay, and we need to evaluate it most certainly. And so again, x squared plus y squared, that's usually a, if by now in calculus 4 or calculus 3, well 3, 4, I forget the semester that we're in, but if that isn't screaming to you polar coordinates, I don't know what is. Okay, so really what we're probably going to make use of is the change of variables r, x is r cosine theta and y is r sine theta. Okay, and then certainly this already imbues a certain understanding, so we know that generally r is going to be between 0 and, well, 1 in this case. That the 1 can change, and then also we know that theta is between 0 and 2 pi. Okay, generally speaking, we might need to adjust that as we go on here. All right. All right, but anyway, we're thinking of a little mapping here. So here's D star, and here is D. Okay, and so we're thinking that, all right, so we know y is between 1 and -1, and this actually corresponds to D, so I'll write it over here. -1 less than or equal to y, less than or equal to 1. Okay, that's fine. And then x is, well, it's going to be between 0 and, well, really x squared is going to be between 0 and 1 minus y squared, or put differently, between 0 and, 0 and 1 if you're looking at x squared plus y squared. Okay, so that's really just going to give us that condition ultimately. But either way, okay. All right, so now here's something that's kind of interesting. If we're looking at this carefully, okay, we're saying that x is strictly positive, right? Because we're saying that x is between 0 and that. So technically, when we're drawing this, while we want to talk about the entire unit circle, and yes, this is a circle, bear with me, we're actually only talking about the part where x is positive. So we're only talking about that part. Okay, we're not talking about the left-hand side. Okay, so really, when we talk about our restrictions, we have to do some adjusting. So r can still be between 0 and 1, that's fine. But the theta, the angle that we're looking at, is no longer between 0 and 2 pi. It's actually between negative pi by 2 and pi by 2 to account for that restricted area. Okay. Now, when we do this, if we look at a different axes now, in D star world, we're looking at an r and theta axis. You could flip them around, doesn't much matter. So we're looking at pi by 2 and negative pi by 2, and we're going to 1, so it's really just this little, this little rectangle that we're looking at. Okay, and that would be the kind of region that we're looking at in D star. Okay, in any case, we still need to do that change of coordinates, or the change of variables rather. So we're going to say that the integral from -1 to 1 of 0 to 1 by square root of y squared of e to the x squared plus y squared dx dy is equal to double integral, fill in the bounds in a moment, and then this is going to be e to the r, and then, oh, we need the Jacobian. Okay, let's get the Jacobian going. So we have, let's see, partial of x with respect to r, is just cosine. And then partial of x with respect to theta is going to be minus r sine theta. And we get minus sine theta here, or sorry, positive sine theta with respect with partial derivative of y with respect to r, and then with respect to theta that becomes r cosine theta. And then when you take the determinant of this, you just get r. Okay, and so this is actually going to hold true in all cases. So then we end up with r dr d theta. Okay, you can reverse the order there if you want to, doesn't much matter. Okay, just make sure that the bounds match, so r goes from 0 to 1, and then in this case we go from negative pi over 2 to pi over 2. Okay, and that's going to kind of be our example. Okay, so and then this next part is a wrap-up or a summary of that. So if we have a conversion where we look at going from, or we use that polar coordinate transformation or change of variables, the Jacobian's always r. Okay, and then that means we scale by a factor of r. And so really what this means is that when we're looking at Cartesian coordinates and then we transform to a system where we're looking at polar coordinates, okay, now I'm going to do my best to draw concentric circles, okay. Here we go. Okay, good so far. Okay, that's pretty decent. Okay, so when we look at a Cartesian system, these, and I'll do a different color, these are all the same size. Same size grids. Okay, but then when we look at in polar coordinates, really what happens to the rectangles, when we look at them here, they get bigger for bigger r. Okay, meaning that we have to scale by that factor of r. Okay, and one caution I have for you is this question, are polar coordinates 1-to-1? And the answer is, well, not in general. Okay, sometimes if you restrict them, you can get them to be 1-to-1. But unless you have, without those restrictions, you might not be able to say that they are 1-to-1. Okay, so again, this video just kind of went through an example where we converted to polar coordinates, and then we summarize those results here. Okay, one more example, and then we'll be done with change of variable videos.